Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's move on to day 2 of our lesson for 8.3.1, where we are exploring functions in graphs and tables. Problem number 119 says examine each of the relationships below. Okay, so we've got about 6 little situations down here. Some of them are tables, some of them are graphs. And your job is to compare the inputs and outputs of each relation and decide if the relationship is a function. Explain your reasoning. Use your definition of a function to help justify your conclusion. If you recall, our definition of a function, which we talked about actually at the beginning and we skipped on problem 118, was that a function is an equation or rule in which every input value or x value has exactly one output value or y value. And we talked a little bit about how you can use this idea of whether or not it's a function or not by thinking of a soda machine where you can have multiple inputs, multiple buttons that produce a Coke. But every time you press a Coke, you expect to get a Coke. If you press a Sprite, you expect to get a Sprite. But if you press a Sprite, this input does not give you a Sprite, but next time gives you a cola or a Coke, you know something is wrong and it's broken and it's not functioning. Okay, so that was the basic idea of what we were talking about here. So we are looking to be sure that every x value has exactly one y value. Okay, so take some time. I'm going to scroll this down. You can pause your video and copy down the table, determine whether or not it is a function or not, and then declare whether it's a function or not and the reason why. Just a brief statement. Do the same thing for all the tables and all the graphs. Spend about 20 minutes doing this, and then when you unpause, I will do the reveals. Alrighty, let's take a look at A. In A, what I'm doing is I'm looking for any evidence at all that you plug in a number, you get a different answer than one that you got before. If there's no evidence of that, we're going to call it a function. So here I've got the number 7 gives me 6. Is there any other situation where 7 gives me a different number? There's no other 7s up there, so we're good. Same thing with the -2, with the 0, with the 4, the 9. We have no situation here where an input value gave you more than one output. So based on this relation, we would have to say it is a function. Every input has exactly one output. Now you look at B. You got 3 gives you 4. -1 gives you -5. A 2 gives you a 9. Oh, but looky there. You got 2 gives you 9, but it also gives you a -8. That's a problem. You can't have that. It's like pushing a Coke and getting a Coke, but the next time you push the Coke button, you got a Sprite. That is not okay. That is not a function. So we will declare that as not a function. The number 2 has more than one output. You take a look at C, and with this one, we're going to use our vertical line test. You can see here, that value for X right there at the far left of the circle would have only one output, but every other value for X is going to have more than one value for Y until you get to this side. So that does not pass the vertical line test, so it is not a function. There are multiple X values that have more than one output. In this case, multiple X values have 2 different outputs. Now looking at D, let's look at each one of these points. There's only one point on that line, so that's good. There's only one point on that line, that's good, that's good, that's good, that's good, that's good. Okay, so one thing that's important to notice, I'm going to go ahead and scroll down here and reveal the answer that is indeed a function. Each X value has exactly one or only one Y value. One thing I want to point out is just because it's a function doesn't necessarily mean that there's a nice clean rule that applies to the situation. So if I took this and it's like, okay, what's the rule that passes through those 2 points? That's wonderful, but those 2 points are only 2 of the 6 points that make up this relation. So in order for there to be a rule, there's got to be like a very specific pattern that happens with all of those points. So I want to make this absolutely clear. Just because there is a rule, just because it is a function doesn't necessarily mean that there's going to be a rule that defines that function. Okay, so let's just be clear on that. Taking a look at this table here, I'm a little concerned about this -8. Give me an 11 here. Oh, but that's okay, because the -8, when I plugged it in again, gave me an 11 again. So this would be an example of like a soda machine that is working. Every time you press the -8 button, you get the same output, a positive 11. It doesn't matter here that your output is a -8. When you press the 11 button, you got the -8. So we would assume anytime you plugged in an 11, you would get a -8 as your output again. Okay, so here we definitely have ourselves a function because every input has exactly one output. And then this one will require the vertical line test again. And this is an example of a function, right? Every single point on that line, here's an x value, its y value is at -2, right? Here's an x value where the y value is at 0. Here is a x value where the y value appears to be somewhere around like 1.7 or 1.8. So we never have a series or a situation where an x value gave more than one y value. So f is definitely considered a function. Right, so for each part below, work with your team. You're working at home watching this, so you are not going to be able to work with your team. You're going to work on your own and create a graph based on the given information. Each part on a separate set of axes. Don't try and do them all in the same one. That's just going to make a huge mess, okay? So you're going to have to take some time and use your graphing paper again. I would recommend that for each one that you set up your graphs with a counting sequence of 1, with the exception of C. For this one, in order to see all the points, I needed to, well, you could still count by 1, just make sure that you make it all the way out to 8 on both your X and your Y axis. I decided to count by 2s, and I accomplished the same thing. So I'm going to go ahead and do the work here while I'm paused. You pause it and copy down each one of, oh, can we see it? No, you're going to have to go back to here. Okay, pause it here. Copy down this table, this rule, and that situation, and then create a graph that fits with each one of those. And then unpause when you're ready to see what those graphs look like. Alrighty, let's take a look at them. So the first graph that I did is an example of one of those parabolas that's tipped over on its side. So it does look like a U shape, but it's definitely not a function because you see here that 1 gives you a 1, and then a 1 again gives you a -1. So that right there, these 2 points are proving that it is not a function. And then these 2 points also prove that it's not a function. So you can't have more than one output for every input. So definitely not a function for A. For B, this is an example of an absolute value function where it actually shows a V shape. So you plug these numbers in, and whatever you get for your difference between those two numbers, you always take the absolute value of it, so you always get a positive. So when we plug in -1, that became -3, but it's the absolute value of -3, so that would be +3. So looking at this, you see the whole vertical line test. That is definitely an example of a function. Now, you might be wondering why I decided to connect the dots here, but I didn't connect the dots there, because this was a table of values. And as far as I know, this is a discrete graph, and those are the only points I was supposed to plot. There's no indication that I should continue with any kind of a pattern and plot anything more, so we're just going to plot the individual points. This is a rule where you can make up literally any value for x. So there's no limit to the numbers I can plug in. So this would be the continuous graph where you actually connect the dots with a straight line. And in this situation, it says starting value of 8 and a rate of change is -2/3. So it doesn't give us a series of points. It just says that's the rate of change. And so, if you think of that slope ratio, I'm pretty sure this one should be a continuous graph as well. I was a little bit questionable about that, but I think it's supposed to be a continuous. At any rate, that's not what this is all about. I did connect the dots. I've labeled 3 points on there. This is definitely a function because every input has exactly one output. Every x value has exactly one y value. And then here, this is an example of a inverse variation, where x and y, when multiplied together, always will give you 12 for an answer. Let me go ahead and kind of show you a variation on this particular function. This could also say y is equal to 12. That's supposed to be 2 there. Hey, no, come on, write properly. 12, yes, much better, divided by x. So this is the function form of it, but this is another way of finding out all the ordered pairs you need. Choose all the ordered pairs where when you multiply x times y, you get 12 for an answer. For instance, this one is 3, 4. This one is where x is 2, y is equal to 6. And this one right here, now let's do this one. This one is 4, 3. So that's the relationship between every ordered pair that is found on this nonlinear graph, is that the product of the x and y always equal 12. And then we often just think about the positive graph, but there would be a mirror image on the other side, where negative 4 times negative 3 would also equal 12. Okay, so notice every x value has exactly one y value. Same thing over here. 3 of these examples are functions. The only one that is not was a. All right, which brings us pretty close to the end here, but I do want to go through and kind of explain why we would use function notation. Now, I'm not going to ask you to use function notation in 8th grade, but it definitely comes into play in 9th grade and high school math. So let's take a look at this. It says function notation is a simpler method of describing a function without a lengthy written explanation. The most frequently used function notation is f of x, which is read as f of x, right? So in this case, the letter x placed within the parentheses and the entire symbol f of x stand for the domain of the set and the range of the set, respectively. Okay, so what does this mean? First of all, the f of x is simply another way of referring to y. So in a two-variable situation, in this example that we had here for b, we said y is equal to the absolute value of x minus 2. But when we refer to function notation, we change the y to be f of x. It doesn't necessarily have to be the f of x. It can be anything, but that's the most common one that we use. So when you set up your input and output table for this particular function, the inputs will still be your x's, but the outputs are now what we call our f of x's. So if you plug in a negative 2, you get a 4 out. If you plug in a negative 1, you get a 3 out. 0 gives you 2, 1 gives you 1, and 2 gives you 0. So this is just some of the possible values that you can get out of this. So if I were to just, now I want to highlight what we mean by domain and range. Once again, I'm not going to be assessing you on your understanding of domain and range in 8th grade, but it will come up heavily in high school. If I were to say, what is the domain and range for this function, the domain would be what are all the possible x values that could be used in this particular function, and the range would be all the possible y values or output values that you could use for this particular function. But because we're not using a y, we're using the f of x, so the range is going to be the collection of all output values. If I only focused on this table alone and just said, okay, forget about the fact that the table is associated with that rule right there. Let's just look at the table itself. All of these would be a part of your domain, and you would just list them as a set of numbers. And all of the output values would be a part of your range. Okay? So when you hear about domain and range next year in high school, this is what they're talking about. Hopefully you'll remember our little conversation here. Okay. So how do we express our answers here? So if you'll notice over here where I had this point, well, hold on for a second. Let's do this one right there. -1 and 3. So when we plugged in -1 for x, -1 minus 2 is -3, and the absolute value of that is 3. We would express it as an ordered pair, or we would say when x was equal to -1, y was equal to 3. Okay? So these two ways are the two ways that you can express your answer. Well, when we're using function notation, instead of saying it as an ordered pair, we will write it like this. And what this basically means is when x is equal to 2, the f of x would be equal to 0, right? So this is referencing that point right there. So we just say the f of 2 is equal to 0. That's the shortened way of saying it. That means the same as when x is equal to 2, y is equal to 0. And then if we take the f of 1, that's like when x is equal, or I'm sorry, the f of -1, when x is equal to -1, y would be equal to 3. So we just say the f of -1 is equal to 3, and it's just a different way of saying it. So someone always asks me this question, why? What's the point? Why don't we just stick with our x's and y's? Well, using function notation does have its benefits, okay? So I want you to reflect back to when in chapter 5 we were working with systems of equations. And one of the last homework problems we had in that unit had to do with mailboxes plus and United Packages. If you recall, they both ship packages like UPS or like the post office, right? But they charge different amounts. So Mailboxes Plus charges you $5 just to ship a package. And then they weigh the package and they charge an additional 25 cents per ounce. So based on the number of ounces that your package weighs, it will change the price. This is absolutely a function, right? Because when you say that you are going to ship a package that is 10 ounces, we would multiply 10 times 25 cents to give you $2.50, and $2.50 plus $5 means the cost, your Y, is going to be $7.50. Here, United Packages, they charge less to ship, but they charge more per ounce. So if you had a lighter package, you might want to go with United Packages. If you had a heavier package, you might want to go with Mailboxes Plus because you're going to end up saving money in the long run at the cheaper price per ounce. And so in this case, if we plugged in the number 10, the 10-ounce package would cost $5.50 through United Packages, and it would cost $7.50 with Mailboxes Plus. But now notice the problem that we have here. When I give you those two ordered pairs, is it obvious which company each ordered pair belongs to? I would say it doesn't. It's not obvious. So what if we decided to change the notation around and do it like this? What if instead of saying y was equal to 0.25x plus 5, we said the m of x is equal to 0.25x plus 5? The m is indicating that this is the function that goes with Mailboxes Plus. And here we'll use the u of x instead of y to imply that for this function, anything that we have that goes with this function goes with this company, United Packages. So now I present to you the same piece of information. The M of 10 is $7.50. We know precisely which company we're talking about. This is how much it's going to cost if you go to Mailboxes Plus with a 10-ounce package. U of 10 is equal to $5.50. This tells us how much it's going to cost when you go to United Packages. If you ship a 10-ounce package, it's going to cost you $5.50. So that's essentially the reason why so many mathematicians like using function notation, because you could have 3 or 4 different rules with 3 or 4 different situations, and by using the m of x or the g of x or the u of x or the f of x, you know exactly which rule goes, or which response here goes with which rule because of the way it's designated. So I think that's it. We have completed our lesson on functions, 2-day lesson. Hopefully you have enough background information now to be successful when you move on to Del Oro. And we are going to start getting ready for our Chapter 8 test where we deal with all of this good information. All right, take care. Bye.
Hey, feeling good, like I should.